Today we'll start with sort of a general introduction to the topic, right, and why it's important. I mean, most of you probably already know about optical fibers and probably know some basic things about them, right? But in this course, we'll study in detail um, how this technology has actually helped. I would say it's probably the most important technology which has enabled the modern internet, right? So the fact that you are able to sit at your computer and access any website posted anywhere in the world. You can stream like high definition videos, right? Anybody can post anything on the internet, and the whole world can see sort of at a click of a button. All that, mostly the most important technology which has enabled that is fiber optics. Okay, so optical fibers have enabled this global connectivity. So you can see that it's very important to know how they work, right? So that's going to be the focus of our course. So let's get started. Right, so let's treat this as a usual classroom lecture. So at any point, if anybody has any question or doubt, just unmute your mic and shout out your question. Okay, just like a normal class. Okay, so as I said, optical fibers have sort of enabled this revolution in information transmission over long distances and global connectivity, right? And so if you look at information transmission, right? So basically, locally we store our data in electronic form, right? So it's stored in memory, in computers or data servers in electronic form, and it's also processed in electronic form, right? Your CPU in your laptop or computers, so transistors, etc. They all sort of manipulate electronic signals, right? So all this is done in the electronic domain, right? But when you want to transmit information from one place to another, right? Uh, in the earlier days, that was also used done electrically, right? So either using electric current or electromagnetic waves at low frequencies, um, but that was very limited. Okay, um, I would request everyone to please turn off their videos to save bandwidth, so that everybody can get to see the board clearly. And also keep your mics muted, and only when you have a question unmute and ask. Okay? Right. So right. So in the earlier days, the information was transmitted from one place to another, and also nowadays also, I mean, more and more of it is being replaced by photonics, where information is transmitted using light. But for many local things, right, like for example, if you have a local, like a LAN or something, most of those connections are still over a small area. Locally, they are still electrical connections, right? So, for example, electronics. So these are connections made using copper wires or coax cables, right? Ethernet cables. These kinds of electronic wires which transmit electronic signals or electromagnetic waves at low frequencies like megahertz or gigahertz, like microwaves. So that's the domain of electronics, right? But sort of over the last 40, 50 years, there has been a push towards transferring all this technology from the electrical domain into the optical domain. Okay, so as I said, the most important technology which has enabled this is optical fibers, which are basically, as you know, like wires for light, right? And so why is this push being to go from electronics to photonics, right? Transmit information in the form of photons, and especially photons which are at very high frequency, like infrared. So the wavelengths we're talking about is like 1 to 2 microns in that range, right? So the frequency, if you talk about the frequencies, it's hundreds of terahertz, right? And so why do we, or why have people been trying to sort of replace all electronic technology with photonic technology, at least for information transmission, right? As I said, for locally manipulating the information, the signal processing, that's still done mostly electronically. Although recently there has been a push to also convert that to the optical domain, right? But that is still ongoing research. But for information transmission, if you look at the current technology, right? So, for example, now you are getting fiber to the home, right? You are getting internet connection at your home directly with the optical fiber coming to your home. Right. So, electronics, as I said, was limited because so the bandwidth for data transmission was quite limited because, so for example, in the earliest days, there used to be these telegraph cables, right? Basically, these copper wires, and information was sent using this current pulses. So, high current will be like bit 1, and low current will be bit 0, and you just turn some switch on and off to transmit the data, right? But that can't be done very fast, okay? And then slowly they were replaced by sort of faster technologies, and then we moved to sort of RF and microwaves, so like the mobile phones, for example. But even there, because the carrier wave is limited to, let's say, gigahertz frequencies, right? The bandwidth here is at max, maybe you can go to like 10 gigahertz, right? And even your electronic components mostly work, right? If you take transistors, for example, they can't work faster than gigahertz frequencies. Okay, so you're sort of limited to these speeds and bit rates if you work electronically, right? But for like as I said, once you go to once you transmit information in terms of optical waves, right, where the carrier frequency now is hundreds of terahertz, right? So now the bandwidth that we can get is huge. Okay, so in principle we can go up to tens of terahertz in bandwidth. Okay, so 3 to 4 orders of magnitude larger than what we can get with electronics. Okay, so that, for example, has enabled now we can like stream high definition videos over the internet, right? That's because we can send a huge amount of data parallelly, right, over optical fibers. Okay, so that's one huge advantage to go from electronics to electronics. The second main advantage is actually losses, right? So when you transmit like electrons over copper wires, I mean it's a good conductor, but it's not a perfect conductor, right? So it has some finite resistance. So I hope all this is visible. So there is, I guess, some reflection on the board at some. So can you tell me what part is sort of not visible? Maybe I can write that again.
Sir, that limited bandwidth part, copper wires.
Right. So. Okay, and yeah. So the second main sort of drawback or limitation for electronic means of transmission is, as I said, like the finite resistance of copper wires, or the finite loss, for example, coaxial cables or Ethernet cables, right? Which also leads to usually some heat dissipation. Okay, and this is also a problem actually in sort of your local electronic data processing units, right? Like for your computers or data centers. Um, this is also a problem there because, like, even on your chip, the miniature wires have some finite resistivity, and uh, like when so many transistors are switching on and off, they release a lot of heat. Okay, so that's a big problem now in sort of computing hardware in general. Okay? But if we go to photonics and transmission using optical fibers, right? Okay, so to give you some idea here, so let's say if we take a coax cable, right, and we plot the loss as a function of frequency. So the typical frequencies that I use are megahertz to gigahertz, right? And if we plot loss here on the y-axis in dB per kilometer, okay, so maybe I'll explain this unit a little bit more. So basically, this is the propagation loss that you get. So if you transmit 1 kilometer, the signal goes down by so many dB. So basically, the loss increases with frequency like that, and sort of it goes between from 1 dB per kilometer to like 10 dB per kilometer once you approach gigahertz frequency. Okay, so that means what? Right. So this dB per kilometer loss, right? So that is defined as, so dB you know is defined as 10 log to the base 10 of the ratio of the powers, right? So input to output power. So your output power is lower than your input power because of the loss, right? So you convert that to decibel, and then you do per kilometer, so you divide by the length over which you send the signal. Okay? So that's how you get this loss in dB per kilometer. Right? So 10 dB per kilometer means your signal gets attenuated by 10 times over a length of 1 kilometer. Okay? So you can see that this is a big problem, right? So I mean, for local connections like within a room or within a building, maybe it's fine. But if you want to send over long distances, like between cities or countries or across continents, clearly you can't do that, right? Because you have too much loss. Now, once you go to optical fibers, right? So people figured out how to make extremely low loss fibers. So ideally, you can imagine, right, like photons traveling through a dielectric medium. If the energy or the frequency of the photon is less than the band gap of this material that they're flowing through, then there should be no absorption, right? They should just pass right through. The material should be transparent, right? So that's the idea, right? So optical fibers, you know, are made out of glass. So people figured out how to make extremely pure glass, right, with as few impurities as possible, and they were able to. So now the state of the art is this loss is down to 0.2 dB per kilometer. Okay, for wavelengths around what is known as, so telecommunication wavelength, or the most popular one which is used is this 1.55 micron. So this is in the infrared range, you can see, or it's called the near infrared actually. The visible range goes up to 0.8 micron, right? And beyond that it's near infrared. And so the loss is actually a function of wavelength. We'll see more about that. But the minimum loss occurs at this wavelength, 1.55 for glass, and the loss can be as low as 0.2 dB per kilometer, right? So you can compare with this. And so now if you look at the frequencies, right? So this is the carrier frequency that we use for electronic signals. But if you look at the carrier frequency for this, right? So you do C by lambda, you see that it's about 200 terahertz. Right? So you move orders of magnitude higher in frequency, and your loss is also extremely small. Okay? So you can get this huge bandwidth because of this high carrier frequency, and also very low. So you can send very high data rates over long distances, right? Which is basically what. this global connectivity and has enabled the internet. Okay, so now you know that, for example, there are transatlantic optical fibers laid under the oceans, for example, right, which run for thousands of kilometers. And that's because this loss is small. Even then, we sort of need repeaters in between to sort of boost the signal, right? So you can imagine if you have a 1,000-kilometer long fiber, the total loss would be 0.2 into 1,000, so that's 200 dB. That's still very, very high, right? So still you need repeaters periodically, but you don't need repeaters very often. So you can have like one every 100 kilometers or so. Right, so if we compare them on the same scale, right, so you can plot frequency here on the x-axis and go all the way from, so this is kilohertz. So the x-axis is on log scale, megahertz, gigahertz, terahertz, all the way up to petahertz, so this is 10 to 15 hertz. And then we plot loss on the y-axis, which is also in log scale, so 0.1, 1, 10 and 100. Okay, so the earliest technology that people use was just copper wire, right? So that's right up here. Very low frequencies and very high losses. Copper wire. So the early telegraph systems, for example, right, were here. Then we moved to slightly better technologies, like so we have coax cable. Right, so the loss is, let's say, an order of magnitude lower, and you can go to an order of magnitude higher frequency. Okay, then you can go to more sophisticated technologies, so like there are these microwave waveguides, where you can go to maybe tens of gigahertz of frequency, right, at like a unit per loss of kilometer, but they are very sort of complicated to make, right, and typically you can't make them for very long lengths, just because the structure is, they're not like wires where you can just make long lengths and bend them and stuff. And then if you look at optical fiber, now we're going to frequencies like very high, hundreds of terahertz, right, and the loss goes down quite a bit. You sort of here. Okay, and this development from like copper wire to optical fiber, you can see we've reduced the loss by maybe 3-4 orders of magnitude, and also gone up in bandwidth, let's say by 3-4 orders of magnitude, right? And this has happened, let's say, over the last 100 years. So yeah, maybe let's look at this brief history of this development, right, over the last 100 years or so, just to get some context, right, of how basically the optical fiber is just a revolutionary technology. Right, so basically we are looking at the history of telecommunication. right? Basically, which means information, communication of information, uh, right? Which is, as I said, locally processed and stored in electronic form over sort of long distances. That's why this tele. Okay, so yeah, so what do we mean by communication system in general? Is like, again, you have some information stored locally, uh, like in electronic form, right, in your computer or data center, and you want to send it to another location, right, where you want to recover this information at the other place, right? So typically, basically, what you have is a transmitter, right? So you put the information you have onto some what's typically called a carrier wave, right? So the transmitter's job is to encode this data onto this carrier wave and then send it over some long distance, which is the channel, right? And at the other end, you have a receiver, which receives this encoded signal on this carrier and then decodes it at your receiver. So that's the most basic block diagram that you can have for a communication system, right? And basically, this system has developed over the last 100 years, right? In the initial days, everything was electronic, and nowadays this part here in the middle is optical, right? Okay, so if you go way back, so 1837, right? Basically, this telegraph was invented. As I said, basically, we use copper wires to transmit electric current, right? And because basically you had to switch electric current on and off, and many times it was just done manually, the speed was very limited, like kilohertz at times. Okay? So 100 bits per second is sort of like the rate you have. Okay, so very slow. So this was invented by a person called Morse. So you might have heard of Morse code, right? So it's named after the person who invented that. So during war times, when they send Morse code, basically it's done manually by a person, right? So they send these dots and dashes. So the speed is very slow. Manually just.
Just that particular line is not visible due to reflection. Just that particular part where you wrote Morse code, the name of the inventor
Yeah,
of
yeah.
telegraph.
The name of the person
Thank
is.
you.
Okay. And then, so the next big advance was the telephone, right? About 40 years later. It was sort of the same technology, but now what we had was like conversion of audio or speech mainly, right? Uh, which was converted to electrical signals. Right? Again, basically just electric current. So there was this there's a transducer, right? So if you look at a landline phone nowadays, it's still based on the same technology. Right? So you have this pressure transducer which senses these pressure waves from the speech or audio signal and then converts it into an electrical signal which is sent over copper wire. So this was, as you know, Graham Bell. Right, and now, so audio signals, you know, like speech or human speech is like between tens of hertz to tens of kilohertz, right? So again, the speed here was sort of, let's say, tens of kilohertz bandwidth. Okay. And then in the same year, very important theoretical advance was made, which was basically the prediction of electromagnetic waves. Right, and also the prediction that they travel at the speed of light. Right, which was very high. It was known at that time, it was already measured at that time to be close to this value. Now we have more exact measurements, but people knew that it was close to 3 times 10 to the 8 already there. Right? So this was, as you know, Maxwell. Right, so he integrated sort of the different equations of electromagnetism, right, found by like people like Faraday, Ampere, uh, right. So they had these separate laws, and then he unified electromagnetism. And in that process, what he saw was that there could exist electromagnetic waves, which are basically oscillations of electric and magnetic fields, which could exist in free space or vacuum, right? And the speed of these waves would be the same as the speed of light. So another consequence of that was what he said was, okay, so then light must also be an electromagnetic wave. Right? So that was a huge insight, right? And then people started to, once this prediction came, then people started to practically generate and detect these electromagnetic waves. Right? So soon after, like maybe 10 years after, the first sort of controlled generation of electromagnetic waves, it was in the radio waves region, right? Long wavelength radio waves. So the wavelength would be like many centimeters to few meters, right? Very long wavelength. So the frequency is like megahertz, maybe kilohertz to megahertz. Right. So these are controllably generated and detected for the first time. So you might have heard about Hertz and his experiment, but actually turns out, which is maybe not as well known, is that here in India, J.C. Bose had also done similar experiments already. So controlled generation and detection of electromagnetic waves. Right, and so once these waves were generated, then people tried to sort of transmit them over distances, right, and detect them over long distances and encode data, right. So this was when radio was invented. These are terrestrial distances. Right, so basically the technology, so even now when you tune into AM radio, this basically the same. Right. So you have some antenna where you're generating these radio waves, and then you encode some data, which is basically audio, onto that carrier signal, and then you transmit that, and then locally we receive it using our local radio receivers. So this was done by another person whom you might have heard of, Marconi. Right, and famously, a few years later, he was able to demonstrate like radio transmission from across the Atlantic, from England to US. Okay, so then basically the radio technology developed a few years after, right? So the AM radio that you guys might not be familiar nowadays, but like all India radio still have AM channels, right? So these are typically like 15 kilohertz bandwidth. So You can encode sort of human speech and music. And the carrier frequency is typically like in the megahertz, 1 to 2 megahertz. You know the carrier frequency by f sub c. Right. So typically, how data is transmitted, you know something about basic modulation, right? So you have a carrier frequency, and then your data, which has some bandwidth, is put on the carrier frequency. Right? So your data has some bandwidth here, data f, which is put on the carrier frequency. So this typically data f is much less than fc, right? So typical values are like 10%. It's usually less than 10% of it. Right, so you can see that as if I make this carrier frequency larger and larger, as the same fraction I can encode data of larger and larger bandwidths, right? Which is basically what is happening as we see the development of the last few. Okay, so then the next big advance was sort of in the mid 1900s was the invention of television. And the transmission of video signals. Right? Right, so even now you have these dish antennas on top of buildings receiving the TV signal. So now, since you have video signals, you need a larger bandwidth, right? So typically, the bandwidth required is about 6 megahertz for like a decent like VGA encoded signal. If you want to go to HD or 4K or these kind of high definition videos, then you require even more, maybe tens of megahertz of bandwidth. Right, so the carrier frequency for these is now higher, like 100 megahertz. Okay, so and around the same time, basically people were able to controllably generate and detect microwaves. So up to maybe like 100 megahertz or so is the frequency, or maybe less than a gigahertz or so. That range is called radio frequencies, right, or RF. And then above a gigahertz or so are known as microwaves. So these are like gigahertz frequency waves, right? And then basically using this technology, sort of in the late 1900s, you had the development of like cellular or mobile networks, right? So mobile phones that we use basically work on microwaves, right? So you have some base station sending microwaves. So typically the carrier frequency is either around a gigahertz, so like 800 megahertz is one carrier band, and then or another one is 2.4 gigahertz. Okay, and then the bandwidths that you can get now are up to like 100 megahertz. Right, so for example, if you see 4G or something, I mean, by the time it gets to your device, the download speed that you can maybe get is like max like few megabit per second. But for example, like if your LAN routers etc. could work at like 100 Mbps. Okay, so that was sort of the state, like at the end of the 1900s, right? Basically, microwaves and radio frequency waves used for data transmission. Right, so you can see all this is electronic technology. right? No optics here. But so even with the development of these cellular wireless networks, sort of, for example, like a base station covers an area of maybe a 1 kilometer square area, right? So if you need to go outside that, then you need another base station, etc. Right? So still sort of the coverage area is limited, and also the bandwidth you can see is limited to, let's say, 100 megahertz, right? So now let's look at the development in photonics, which sort of led to this transfer of information. Slowly people started using light, right, or optics for information transmission rather than this electronic mode. Okay, so the first main sort of advance in optics was in 1960 when the laser was invented. Right. So what is a laser? Is basically, like a very pure coherent monochromatic wave. Right? So it's like a carrier wave. Right. So what's a carrier wave is basically like a single frequency wave, right? But now the frequency of this carrier wave is very high. Right, so the first laser that was invented was the ruby laser. It was at red wavelength around 680 nanometers or something. So the frequency here is about 500 terahertz. Right, so suddenly there was a way of producing carrier waves which was 4 or 5 orders of magnitude higher in frequency than what people had achieved. Okay, so this was done by Mayman at Bell Labs. Actually, one interesting story is that Mayman didn't get the Nobel Prize. So people who got the Nobel Prize for the laser were the people who had theoretically predicted the laser, but the guy who actually built it practically didn't get it. Okay, and then immediately a few years later, there was this proposal to use optical fibers made from glass, okay, for guiding lights. Okay, so basically if you look at the original paper, it has many of the things that we're going to learn in this course about optical modes, and basically how you can make a wire for light. And not only that, like it can almost be a perfect wire, right, with no loss. So this was done by Charles Cow, who got the Nobel Prize in 2009, or maybe later. I'm not sure about the year. Maybe it was, I think it was later, maybe later, 2014 or something. Let's check the year. Okay, so basically, very two important components of this communication system here, right? So we want a transmitter which can encode information onto a carrier wave, right? So if you want to go to optics, we need a way to generate carrier waves at the optical frequencies. That was the laser. And then we need to transmit over long distances with low loss. That's the channel, right? And that was the optical fiber. Right, and then immediately people realized that what a great technology this can be. So immediately a lot of people started working on practically trying to make optical fibers, right, from glass. And so in 1970, sort of like the first kind of practically usable optical fiber was demonstrated with the loss of about 20 dB per kilometer. Right? So this was already now better than any electronic cables that we had, or at least comparable. This was done by 3 people at the Corning Glass Company. This Corning is a very famous glass company which makes all kinds of things out of glass. Okay. And particularly for information technology, they also make optical fibers of high quality. Okay, and then over the next few years, basically the loss, basically people try to improve the technology more and more, and sort of in the late 80s, this loss of 0.2 dB per kilometer, which is now almost at the theoretical limit. Okay. So we'll see like what are the loss mechanisms that can happen in optical fiber, and if you have ultra pure glass, no impurities at all, right? Even then, there will be a small loss, right? So, I mean, you might naively think that, as I said, like if you have an electric with some band gap, and if the photons have energy less than the band gap, they should just pass through. The material should be transparent without any loss. But it turns out there is some loss. But and that's fundamental, right? Even if you have 100% pure glass, there will be that loss, and this is almost at that limit. So we can't, even with improvements in technology, we can't really do much better. Like the technology is already as good as it can be. And then parallelly, what happened was, so if you look at this communication system here, right? So if you want to develop like a global internet, for example, you need all the components here, right? So with this, basically, we got a almost perfect channel, right? And with the laser, we have a transmitter, but other things need to be done. Like for example, how do you convert the electronic data here into the optical form, right? So that is known as electro-optic modulation, right? So parallelly, what happened was, I guess you can call this coincidence, or maybe people, this sort of different fields coming together towards a common goal. But sometimes, this happens that many technologies are initially promising, but they don't take off because they don't have the supporting technologies which develop simultaneously. But in this case, all the supporting technologies also develop simultaneously. Okay? So, which is what enabled this sort of internet boom in around 2000. Okay, so what I'm talking about is like, for example, repeaters or optical amplifiers. So as I said, if you want to go to hundreds or thousands of kilometers, even with this low loss, you will still need to boost the signal periodically, right? And if you can do that in the optical domain itself, then that's great. You don't need to convert to electronics and then back, right? And then electro-optic modulators, as I said, to convert the information from electronic to optical form. This was also developed and like high speeds were demonstrated, tens of gigahertz. Right? So global connectivity with so long fiber networks were laid down under the sea and under the land, etc. Almost every place on Earth was connected. So, as I said, so around 2000 you have this global internet, right? So we can transmit now, for example, 100 gigabit per second on a single wavelength channel, right? Which means like you take a laser of a particular frequency, right? So one particular FC, and you can transmit data with people have demonstrated up to 100 gigabit per second on a single channel. Okay. You can see this is like 3-4 orders of magnitude better than what we can do with radio waves or microwaves, the wireless channel. And then people also figured out how to send multiple. So the nice thing about this optical fiber is that it can support multiple modes at different frequencies, right? So you can send multiple wavelengths which actually don't interfere with each other. Okay. So that's a big problem in, for example, our mobile networks and RF transmission, is that there's a lot of interference, okay, from background signals, noise, etc. But because these optical signals are at such high frequency, there is actually no other noise to interfere with them. Okay. And you can also send multiple wavelength channels which don't interfere with each other. Okay, so that technology is called WDM, or wavelength division multiplexing, right, to send multiple wavelength channels. And you can encode data on each wavelength channel. Right? So with this wavelength division multiplexing, people have gone like to few terabits. People have already demonstrated commercial systems with like few terabits per second data. Okay, and then still people are trying to push this further and further. Okay, because as you know, the demand for data and is increasing. People want to see more and more movies on Netflix or whatever, right? So the internet traffic keeps increasing. So people are trying to push this further and further. But you can see that how much of an advance this already is over electrical or electronic means of information transfer. Okay. So yeah, that sort of, I hope, gives you a nice background on how fiber optics has enabled basically the information technology revolution, or a big part of that, right? Okay. Okay, so the main focus of this course is to understand how this optical fiber guides light. Right? How does it act as a wire for light? That's sort of our main focus in this course. Right. So basically, we need to see, and again, light is an electromagnetic wave, right? So we need to go back to basics and basically start from Maxwell's equation. Right. That's our starting point. So I guess most of you should have seen this in your prior courses already, right? So we start from the Maxwell's equation and then go to a electromagnetic wave equation, right? And then use that wave equation in different geometries, right? So typically, maybe mostly you would have seen that in free space or in some homogeneous medium, right, with particular refractive index or something. But now, when we try to structure the medium, right, like for example, an optical fiber, consists of some like core region which has some refractive index surrounded by another cladding region which has another refractive index. So when we start structuring the medium through which the light is flowing, then basically we need to solve that wave equation in this structured medium, right? And then we'll see how it gives rise to, for example, the concept of modes and what are the properties of these modes and how light is guided. And so basically we'll start with Maxwell's equations. We'll be looking at, of course, source free. So we don't have any charges or current, right? These are dielectric media. Which means there is no conductivity, right? So dielectric. And it's also not magnetic. So the relative permittivity. Right, so for example, glass, which optical fibers are made out of, has these properties. Right? So recall the Maxwell's equations, four of them. Right, so the four Maxwell's equations, and so E and B are the electric and magnetic fields. This H and D are related to the electric and magnetic fields, right? So B is 2 times for a non-magnetic medium, it is V naught, the free space permittivity. Right, so H is sometimes known as the magnetic intensity. Right, so it's basically the magnetic field scale in some other units, and then this displacement field D related to the electric field by this permittivity. Right, so this epsilon sub r is the relative permittivity or the dielectric constant. So one note is that this is for a linear isotropic medium, right? Which means, so linear means that the relationship between these fields is linear, right? So E and D, there's just a constant relationship, E and it's also a constant relationship. And this is fine for most cases, okay? And especially for our purpose in this course, basically we're looking at just fields propagating through the medium. But in some special cases where the intensity of the light traveling through the medium becomes high enough, then actually this relationship doesn't hold anymore. Okay? Then you can have some nonlinear terms, so like E square, etc. Or another way to think of it, this epsilon also depends on electric field. Okay? So once you go to high intensities of light, then you have nonlinear terms, but that won't be our concern in this course. So that's why it's linear. So for most purposes, the linear analysis is fine. And isotropic means that basically like the B and H or D and E are parallel. It is just a constant. But you can also have non-isotropic media where different directions actually look different. Okay. So then this would be a tensor. So D and E, for example, won't be parallel, right? So this will have two indices. So for example, D in the x direction could depend on E in the y direction. Okay. So those would be anisotropic media. But again, for our case, we basically consider isotropic media because our main concern are optical fibers, which are made out of glass, which is isotropic. Okay. It's an amorphous medium which looks the same in all directions. Okay, and another you might hear is homogeneous medium. So homogeneous medium is again where this is a constant. So mu r is anyway 1 because we are considering non-magnetic, so forget about this. The only place where we'll play games is with this dielectric constant. Okay. And so if it's homogeneous, this means that basically epsilon r is a constant. It does not depend on motion. Right? Whereas non-homogeneous medium which we encounter some in a few cases in this course. So for example, this is a function of position. Okay, so the dielectric constant or you know that the refractive index is related to this dielectric constant, right? That varies with position. So that would be a non-homogeneous. I think we are all out of time, so we'll stop here, right? So next class, tomorrow we'll sort of derive the wave equation from the Maxwell's equation and first look at just the simplest solution in free space, which is plane waves, you already know, and then maybe discuss about total internal reflection, which is sort of the basic principle on which light guidance happens in fibers and waveguides and optical waveguides in general.